One. Good day, everybody, and welcome. Welcome back from your lunch, if that's where you were. And I'd like to thank you all for joining us and joining DevConf. Before we get going, like everybody, I'd like to thank our sponsors. Without them, this event wouldn't be possible. We'd like to thank you guys as well for sticking with us, even through all the craziness that's happened. For those of you who don't know, my name is Michael Johnson. I am a Microsoft MVP for Data Platform. And today I'm going to be talking about a quick introduction to a graph database. So just what we'll be looking at today. Well, first we'll be discussing what is a graph database. It's slightly different to perhaps some of the other databases you've used before. Then we're going to have a look at using a graph database, and I'm going to use Neo4j, which is probably one of the more popular graph databases, but there are several other variations. And then we're going to look at finding out our Baker number, which is really the topic of this talk. And a quick hint, we're not going to solve for the Baker number per se. All right. Okay, so what kind of databases do we have, right? So when most of us talk about databases, we often think of relational databases. Okay. These are databases like SQL Server, MySQL, Oracle, and these work with traditionally table structures with relationships between them two, and they enforce a lot of what we call constraints. Okay, so we have to build all these rigorous rules as to how data matches, the data types it must have, and there's very little room for perhaps going from that agreed schema, right? So there has been a bit of a pushback against relational databases because of that inflexibility. So then we started getting some of the NoSQL databases, okay? And one of the more common NoSQL databases is the simple key value store. The key value store is simply a value that is given a key, often that's hashed, and then a value. So the developer would look up a key and then return the value. Okay, those can be really powerful, but perhaps not all that sophisticated, right? They have a limited use. So then the third kind of database we often see is a document database, and document databases are sort of fairly popular, or they have grown in popularity because everything is stored as a document, commonly JSON files, but they can really be anything. They're essentially just blobs, and like the key value store, we can essentially submit a document and retrieve it, depending on the document database implementation. Something like MongoDB probably being the more popular one, we have this ability to sort of create relationships, not in that way, but we can enforce constraints across the model using these sort of things. So we've got this sort of happy medium between a key value and a relational store. The type of database I'm going to be speaking about today is a graph database. And graph databases are slightly different. When we think about a relational database is often based on set theory. This was made famous by T.S. Codd, and it had a lot of rules. Okay, and just like relational databases have a mathematical underpinning, so do graphs. And this comes from what we call graph theory. And graph theory is this idea of we have nodes and we have connections between these nodes. Okay, and these are sometimes called relationships or edges. All right, so if we want to visualize maybe what that might look like, and this is going to lead up into the sort of the bulk of the talk. So let's have a look. We begin with a node, and a node is just a object within the database. Now, this is not I don't think of it as a table, but it's more a row within a table, but there is no concept of a table. Okay, so we have a node, but a single node database isn't particularly useful. So often we go and place an additional node, and we build out some more nodes until we have a whole bunch of nodes. But ultimately this is pretty useless. So the first thing that we want to do is be able to bucket these nodes in some useful way that makes them queryable by us, okay? So the very first thing we actually have is this ability to create what we call a label. So labels are the type of node that we have, and we can allocate these. So in my very simple little database over here, you can see I have 3 actor nodes, 2 movie nodes, and 1 director node. And we've now got this ability to sort of query them. And we'll discuss the query language in a second. And obviously, labels aren't particularly sufficient. The next thing we need to be able to do is give attributes to these nodes. Okay, so an attribute is simply a collection of properties. Unlike SQL, it is not a relational database, should we say. These are not rigid columns. So very similar to a key value store, where we can provide a number of attributes to this database. So obviously we would think about having possibly movies, would have things like a name and a release date. The next thing we'd want in a relationship or in our graph database is we want to know how these things interconnect. And that interconnection story is really important, because that's why graph databases are powerful. This notion of just nodes, that's a document database. It's those relationships that give us something special. Okay, Donovan, I'm just getting a lot of feedback on. I don't know if that's okay. So we've got these attributes, and then we're going to go and create relationships. And relationships obviously span between nodes. And it's important to realize that these relationships or edges also have a direction. And this becomes pretty important because an actor certainly acted in a movie. The movie didn't act in an actor, if you will. So Donovan, I've just got a whole bunch of noise coming through. I don't know what that is. Okay, sorry about that, guys. Okay, so like we had attributes for a node, we also have attributes for relationships. If we go back into the movie example, well, when Robert Downey Jr. acted in this movie, he played this character, right? So there are certain attributes that we'd want to add to those relationships. If we think about another example, let's say employees and companies, we'd want to have a relationship between that employee and the company, and then in that relationship, we'd specify when they have a when was their start date, when was their end date, perhaps what role they filled. All of these sort of attributes would go into that database. I'm just going to be quick. So for those of you guys who don't know, we're also using the Slack channel. Okay, I see some of you guys are commenting that you also heard the noise. Okay, so if you guys have any questions, you can type them into the Slack channel, and Donovan is our tech lead from Ant. Okay, so we were, sorry, just get back to that. Okay. Yeah, so we've obviously gone and created nodes, and we can go and add additional nodes. And it's important to realize that we don't just have a single direction node. We can actually ascribe multiple roles or relationships between any two nodes. Okay, and relationships can come one way and they can come back the other way. We also have the ability to ascribe multiple labels to both relationships between nodes and edges. Okay, and this can be useful when we have multiple categories. Now, there's obviously some amount of debate as to exactly when you should be using labels versus labels versus attributes. But generally, you want to err on the side of an attribute until you know that you're actually going to, are you going to be grouping by this thing, right? And then that's when you would want to consider a label. Okay, so we're going to get started with our sort of graph database now. And before we sort of get going there, we're going to discuss a couple of routes. Okay, so if you, like myself, probably work in a shop that already has a relational database, a lot of relational databases now actually support graph databases within them. So Microsoft SQL supports it. Oracle has support of it. I believe MySQL also has support. That's probably your easiest entry. But these are not genuine graph databases, and they make a number of compromises, right? They've still got that rigidity in the how we create the nodes and how we create the edges. So if you're looking for flexibility, you're probably not going to go for the SQL, the relational SQL implementation, but that's how you can get started. The next option is going to the cloud. Okay, so two of our platinum sponsors actually provide a cloud. So we have Cosmos database, which is Microsoft's implementation of a document database, but it actually supports what we call the Gremlin API on top of it, turning it into a graph database. And AWS has Net2. So both of these can be fast and scalable ways of getting started. And then finally, we have Neo4j, which is what we're going to be looking at today. And Neo4j has a couple of variations. It has a desktop application as well as a server application. I found it really easy to get started. You just go to the website, sign up. They'll send you a key, you download, and you can get going. Now, each of these interfaces support slightly different query languages. Okay, so as we'd expect, relational databases would use a T-SQL or your SQL equivalent. Okay, so Microsoft SQL Server uses, the typical select star from, and then we've got this additional semantics when we come to the where clause. Okay, then on the cloud, we've also got Gremlin. Okay, so Gremlin is probably one of the more popular sort of query languages. And then finally, we have Cypher, which is what is used by Neo4j. Okay, I just have a question. What is the benefits of a graph QL database and a relational database? Okay, so why would you use the one? Well, its biggest flexibility, or two things, right? So one is we've got that flexibility. Relational databases have that rigidity to them that a graph database doesn't necessarily have. Okay, but its biggest attribute is when we are concerned primarily with what we would think of the nodes, okay, the data inside tables, relational databases might be better. But when we want to actually understand the relationship between these nodes, okay, that's where the true strength of these graph databases come in. Okay, it becomes really easy to span multiple tables, passing through different relationships. That can get very complex in SQL Server. I'm sure everybody's, or many of you have probably seen a table that's been joined onto itself like sort of 10 times. Okay, that is not performant. It's just not good design, right? So we want to avoid things like that, and that is what graph databases deal with really well. So if the relationship is what you're after, try to go for a graph database. Okay. Let's check the questions. Okay, so we're going to get going with Cypher. Okay, so time for a quick demo. I'm going to stop sharing my slides with you. Sorry about that button. All right, okay. And we're going to get going with Neo4j. So as I said, I simply went to the website and I downloaded it. And this is the desktop install. Okay. Now what I've done is I've created two databases. I have an IMDb demo, which unfortunately we won't be using today, but I have the getting started database that we will. So it's really easy to get started. We're going to use the Neo4j browser, which is a sort of a console tool, but a really friendly one to get started. You can obviously choose pretty much your favorite API to connect to it. Okay, so I'm going to manage. Okay, you'll see some of the connection details, its status, some of the port information. We're going to go and open the browser, which opened up on my other screen. Okay, so this is the Neo4j sort of experience, okay, through the browser. It starts up with some really handy little tutorials. So this is just some sort of connection information, but these little tutorials are great getting started guides that show you how to go and build your first graph database. It also shows you how you might ingest data from a relational database, and then obviously some monitoring tools. So we're not going to do that today. We're going to begin creating our graph database. All right. Okay, so in our little slide presentation, the first thing we had was a node. Okay, and we're going to go and create exactly the same thing. So we're going to create, and create is that statement for create a new thing. And we're going to go and create this node, and n is just an alias. Okay, so you'll see I'll use different aliases. They don't mean anything. They're just references to the thing. Okay, so create n will create a new node for me. What I would like to do is then I want to return that node. So I'm simply going to say, okay, so I'm going to go and return that node I just created. So when I run this piece of code, I'm going to get this run, and you can see that I've got this little node that sits on my screen. Now, this is not a particularly interesting node because it has absolutely nothing associated with it. It was exactly like that node that we had earlier. So just want to go through a couple of other fundamentals. The next thing we want to do is we want to go and find all the nodes. Now, exactly like here, I have one node. I can go and search for all nodes. And when we search in SQL, we do a select from, okay, within Cypher, we use the match statement. Okay, and match just goes and provides some sort of criteria. And I'm going to say, go and find everything. Okay, so kind of a very brute force approach. So go and find everything and then return everything. So exactly like we had earlier, we've got that node returned. Now, this is not particularly useful. So if we want to complete our CRUD analogy, okay, so we've created this thing, we have search for it, and now we want to delete it. So I can go and find that match, and I can go and say, I'm going to delete, and I'm going to delete that node. Right, so now we have an empty database. Okay, let's have a quick look for questions. No, okay. Apparently a couple of people are having audio problems, but they're gone now. Okay. All right, so we've now gone and created our node. I'm just going to do a little bit of housekeeping here, and we're going to go and create a slightly more useful node. Okay, so we're going to go and give it a label. So we're going to say, I want to go and create this node. I want to give it that label, and we simply do that with the semicolon. Then we say, what kind of node is this? Okay, so we're going to go and create a person node, and we're going to give it that alias, so I can refer to it again. And then return our alias. Okay. Oh, some people cannot spell create. Spelling is hard, guys. Yeah, this is why I have a copy and paste list as well. Okay, here you can see our node slightly differently. The query syntax says that we've got one node existing in this model, and it is of type person. You can see that we can interact with it. Again, it's not particularly useful. So we're going to go and delete that guy once again, okay, and we've got an empty database. So we're going to go begin our creation of perhaps a more useful database, and as you probably got to guess, we're going to use movies. So the first thing I want to do is I want to go and create a node, and the type of node I'm going to create is a form. So this is the label. We're going to create an alias. Okay, we're going to call it M, and then we're going to go and provide a set of attributes, and we simply create a basic JSON object for that, right? So it is a name, and we give it a name, Pulp Fiction, as well as an additional attribute, which is year, and that's going to be an integer, which was 1994. So that's the year the movie got released. So we're going to simply go and create that movie, and we have this new node. Okay, so again, we can see that we have one node of type form. If we interact with it, we can see the properties. Okay, so we have the name and year. Just a little tip. So I come from a sort of Microsoft background where a case generally doesn't matter. If you use the attribute label name with a capital N, you won't get this handy little the name being shown in the middle of the node. Okay, all right, small ones, right? Okay. So we've now gone and created a form, but as we know, the form actually had a couple of actors. So the next thing we're going to do is we're going to go and create two nodes. And this shows us that we can actually create nodes multiple nodes at a time, right? So we don't have to do a single lookup every time. We can create two nodes, both of type active, although we can actually create additional nodes. They don't all have to be of the same label, okay? And then we're going to give them a name. Obviously, if we were to build out something more useful, we would probably want to include more useful information, possibly such as the date of birth. If we think about the IMDb database, it includes spouse information, where that person was born. All of these kind of bits of information that you would want about the data. Right. So we're going to quickly go and we're going to go and create our two nodes. And here you can see that we've created those two. So if we want to see what our entire database looks like, we're going to use our match statement. We're going to call it a node. Okay. So you can see that we've got our three items, but they're missing relationships right now. Okay, so relationships are obviously key. So before we do that, we're going to create one more node, and this is going to be the director. Okay, so we all know that, well, I suppose some of us know that Samuel L. Jackson and Bruce Willis acted in the movie, but there was another actor, Quentin Tarantino, who also happened to be the director. Okay, now I have created this as a label. Okay, so we're going to go and create that. Sorry, can't cut that. So let's go and run that again. And here we can see our heroes. So although we've tagged Quentin Tarantino as a director, there is no relationship between himself and Pulp Fiction. Okay, so that's what we're going to do next. So how do we go and update an existing node? Okay, and first, the only way to do that is we need to actually get a reference to it. So in order to get a reference, we're going to use some of that sort of select syntax that we use, that match statement. So if we say, I want to go and match, all the, let's call them films, but, okay, so full, okay, and then we're going to return if. Okay, so this is going to go and search for all the films, and it's going to return them. Okay, so now you can see that we're not returning all of the nodes like we did previously. We're only returning those that are of this type of label. Okay, and we can do exactly the same thing with the actors. Okay, so I'm going to match, let's say an actor. And this time what we're going to do, okay, break. Okay, we're not going to return the node itself. Well, we just want to return a property. So let's go and add the name. Okay, and by running that, we don't get this this handy sort of graphical interface anymore, because all we're doing now is actually returning a sort of JSON object, right? Or this is actually tabular structure. Okay. So, this is all that sort of information. Okay, so now we kind of know how we can limit our set on a label. We can also add a similar restriction using some of the attributes. So here I'm saying I would like to return all of the actors, but I would like to filter. I would like to also where the name is Quentin Tarantino. Okay, so this is going, when we run that, it's going to return me that object. Here you can see that this object has been returned as a JSON type, and we get Quentin Tarantino. Okay, so now we've got this ability to, or now we've figured out how to actually gain a reference to an existing object. Okay, and we're going to need this to create relationships. So we're going to begin by, I'm going to go and create a relationship between my two objects, and just go and bring them all up again. Okay, so these are my objects, and I want to gain a relationship between Quentin Tarantino as well as the film that he directed. So we're going to begin by running a match. Okay, so this will return me the two objects. Okay, I've given Quentin Tarantino, the actor, an alias of A, Pulp Fiction, an alias of B, and we'd like to then go and perform some functions. And what we're going to do is we're going to go and create a relationship between the two. And now the syntax for the relationships is we use a round bracket for the node, as we saw when we created. Okay, and we're going to say I want to go and create a relationship between A, okay, which we know is Quentin Tarantino. I want to create a relationship, and that's specified by the square brackets, okay? And exactly like I did earlier, I'm going to apply a label, okay? Again, we don't need to apply labels, but it's a good idea. And we're going to use the semicolon, exactly like we did with the node, and then we're going to say that he is the he directed this film, and then we're going to specify a direction. Okay, you remember that all relationships within Neo4j do require a direction. So we're going to say that Quentin Tarantino directed Pulp Fiction. Okay, because it would be incorrect to say that Pulp Fiction directed Quentin Tarantino, right? Okay, so we've now gone and created that relationship. I can go and get that detail. So if I go and give this R relationship, let's go and return R. Okay. When we run that, we can see that sort of relationship. It doesn't obviously have any sort of properties to it, but we've created it. So I'm going to go and run this command again. Okay, and now we can see that Quentin Tarantino has indeed been directed, or he indeed directed Pulp Fiction. All right, so something moved, go and check that. Okay, so just some stream issues. All right, so we've now gone and created a relationship between Quentin Tarantino and Pulp Fiction. Next thing we want to do is we want to go and add more relationships. Okay, now just because this data set, I've created this data set specifically this way, I know that Quentin Tarantino, Samuel L. Jackson, and Bruce Willis all acted in the movie Pulp Fiction. So when I go and grab those relationships, I don't just have to go and search for specific actors, okay? Remember, I can use the set, okay? So I'm going to go and say, go and return me the set of actors, okay? So all nodes that have a label actor, and then I would like that I'm going to go and grab my reference to Pulp Fiction. Then I'm going to go and create a relationship from all nodes in that set to the movie B, right? And we're going to go and add the attribute acted in, right? So when we run that, you should see that we now have a relationship between all four nodes. So that is 3 actors and 1 film. One thing to note, not that it's particularly important, is you'll notice that 3 and 1 don't actually equal 5, okay? And that's just because we have the one node that actually has 2 labels, okay? Next up, what we want to do is, you can imagine that doing this would take a long time, all right? So we can actually create multi-statement queries. So I'm going to bring in this one, and let's just walk through that. So here we can see exactly like I did earlier. I'm going to go and find the relationship to Quentin Tarantino, giving it the alias QT. Pulp Fiction, the alias PQ, like PF. Okay, so these are existing nodes that I now have a relationship to. I'm then going to go and create 3 new nodes. Okay, 2 that are actors, so Uma Thurman and David Carradine, and then a film, which is Kill Bill Volume 1, right? And exactly like previously, we've given them attributes. Okay, then I want to go and create relationships between my new nodes, okay, and my existing nodes. So we're going to say that Uma Thurman acted in Pulp Fiction, and Uma Thurman acted in Kill Bill. Okay, David Carradine didn't act in Pulp Fiction, but he did act in Kill Bill. So we're going to go and create that relationship. We're also going to add a relationship that says Quentin Tarantino directed Kill Bill. Okay, so to match our idea of director that we had earlier. And then finally, we're going to go and create a relationship that says that Quentin Tarantino wrote Kill Bill. He also wrote Pulp Fiction, but also that Uma Thurman wrote Kill Bill. So they were co-writers. Okay, so here we can see we've got a fairly rich tapestry of relationships. Okay, so we're going to go and sort of run that. And then we can go, let's go and rerun our view. And we can see that we have a slightly more interesting graph. with a whole bunch of relationships that are of different types. Okay, so we have our actors, we have our movies, okay, as well as associated relationships. Okay, so you can see certainly Quentin Tarantino, he was very involved with a movie like Pulp Fiction. Okay, I'm just going to catch up on the questions very quick. Would I not? Okay, so Quentin from Kevin, would you not want to match Quentin using the director label instead when creating a directed edge? Would you rather match Quentin? I'm not 100% sure what you mean there, Kevin. I think that's kind of what we do. We have the edge marked as a director. Maybe he did put in some specific comments there. Oh, okay. All right. Okay, so the question by Kevin was, would I not want to match on Quentin Tarantino, the director, and not on the actor? So if we go back, this is the query he's talking about. Okay, here you see I matched on the actor Quentin Tarantino. There is no difference between these two nodes, right? So I agree with you, that probably would have been logically more correct, but it's not necessarily wrong. We have two ways of referring to that same node. Okay, so certainly correct, but yeah. Okay. Always been interesting being debugged live, right? Okay. Okay. So next question is Graham. Is there an ability and need to create indexes as you would in a relational database? Yes, you would. So as these things get bigger, you would certainly need to index them. I think that's sort of true of most systems. I know certain things. So if we think about CosmoDB, I know that's not an active operation. They sort of behind the scenes build those indexes for you. But yes, indexing is something that you would need to certainly do with larger data sets. Okay, so we've now gone and created our nodes. Just have to figure out where. Oh, okay, so I've lost my place because we went back. Okay, so we've now got our basic graph, and we're going to start querying this graph. So we're going to pick on Quentin Tarantino again. So what we'd like to know is what movies has Quentin Tarantino acted in, right? So we're going to begin. I'm just going to paste our query over there. Again, we're going to start with matching on a node. Okay, so we're going to identify that actor called Quentin Tarantino, and we're going to give it the alias A. We're then going to go and ask for all relationships that is acted in, right? So we're not looking for directed. Okay, we know he directed more films than he acted in. Then I want to return that set B. Okay, so when I run that query again, I'm going to get Pulp Fiction back. Okay, now if I wanted to ask the same kind of query, I could ask. We could ask for ones that he directed, so that would give us a list. Or we could actually ask, I'm not actually terribly worried about how his relationship, what his relationship to that node is. I just want to know that there existed some kind of relationship. All right, and that obviously it's exactly the same set. Okay, so we've now gone and returned a set of queries that he's sort of acted in. We're then going to go and I want to get an understanding of who his co-stars are, right? So exactly like we saw earlier, we came back with the set of movies that he's acted in was only Pulp Fiction. So when we go back to our graph, we're interested in the people who acted in Pulp Fiction, right? So we don't expect to see David Carradine because he didn't act in that film. He did act in a movie related to Quentin, but not as a co-star per se. So we're going to go and run that match. We're going to say, from Quentin, go and give me all the movies that he acted in. Then from that movie, I would like to return everything that he, all his co-stars, right? And what's going to happen is our data set comes back empty. And the reason is this, is something that you always need to remember, is that these these nodes have directions, okay? So we can see that when you acted in a film, there is no returning graph, right? So there's two ways to do this. What some might do is add a return node. That return node would say that Pulp Fiction featured Quentin Tarantino. So then I would be able to traverse back that way. But the other way is to simply say that I'm not interested in the direction of the graph. So I'm just going to go and get rid of that little little greater than sign. And essentially now we're going to say, go and find everything. So go to that movie and search for all relationships. Okay, now you would obviously need to be careful depending on exactly what kind of relationship, because if we did need to know acted as opposed from any interaction, then we would probably need to have something like a featured relationship going in the other way. Okay, so if we quickly run that query, we can see that these are his co-stars, and obviously quite interesting that Quentin Tarantino is obviously, it makes perfect sense because we're going and saying, give me all the actors in the movie that he played a role in. So Quentin Tarantino is indeed one of his own types. Okay, so I'm just going to come back to the questions here. Is it standard practice to match on logical keys? In this example, the name of the actor is an artificial ID. Okay, so the question is, should we match on something like the name, okay, or should we use the artificial name? So what you might have noticed is when I actually click on a node, you'll see that every node is actually given an ID. I would suggest that you do not use an ID because these IDs are not, they're not guaranteed in any way. They're actually randomly assigned. They're not even sequential, or at least that's been my experience of them. So I would not take the approach of using the ID in any way. Okay. Next question, again, I guess is the first question how does Neo handle primary keys? Okay, so you can create a unique constraint on an object, okay, which would give you the notion of a primary key. It doesn't necessarily have the same meaning as a primary key in a relational database, but it has that enforced uniqueness. Okay, but there is no restriction on on what we might think of being the foreign object back to that object, because obviously it must exist for you to create a relationship to it. There isn't that notion of having a referenced table without that node, because you're actually pointing at the node itself and not at the table itself, right? So it's not a primary key that supports a foreign key, but it is a unique column. All right. Next question: is there a way to define types similar to the table structures in a relationship? So these are flexible objects. Okay, so exactly like we'd have in a document database, we can impose a schema on node types. So I think that matches what you're asking. But also we don't have to. So we can create these things as we see fit. With different sort of data types. So that obviously we can mark different things as data types. So strings, integers, dates, etc. So we can do a lot of that. Obviously, one of the things that they're trying to avoid here is perhaps the rigidity of a relational database, but we can conform to that schema. Okay, so what we did here was we got a list of his co-stars. Okay, and the next thing we really want to do is, or this is sort of why we kind of started, is sorry, I've just got another question here. Docker wants to update, of course, we'll run now, right? Okay, so the thing that we're trying to solve for here is trying to figure out the Baker number. So for those of you who don't know what the Baker number is, it's essentially the distance between any two people is how, the degrees of separation, if you will. So Kevin Bacon is deemed to be a prolific actor, so sort of the center of the universe, if you will. And it was thought that everybody on the planet has essentially 6 degrees of separation to Kevin Bacon. So we're going to use our data set. Now, I don't have Kevin Bacon in my data set, so we're going to pick on David Carradine. Okay, so let me just go back to and go and clean up some of these queries here quick. So we're going to run this guy again. Well, that's actually just going to return that graph. Okay, so this is our notion. And what we'd like to understand is we want to understand the distance between these sort of two actors, right? So we're going to go and create a reference to Samuel L. Jackson, and then we're going to go and create a reference to David Carradine. Okay, so here we can see Samuel L. Jackson over here. We've got David Carradine over there. And we want to know is how can we traverse from this point, okay, to David Carradine. So Cypher supports a function called shortest path, and this is a standard mathematical function, okay, where we look for, given the various routes, because if we think about Samuel Jackson, I'm just going to let's go down and see this. We can pass in one of two ways. We can either go from Samuel Jackson into Pulp Fiction, to Quentin Tarantino, to Kill Bill, or David Carradine, or we can pass from Samuel Jackson, Pulp Fiction, Uma Thurman, Kill Bill, and David Carradine. Right? Okay. Now these both happen to have the same length, but you can see that there are multiple paths available to us. Okay. So the shortest path function is we're going to use that, and we're going to give it a set of criteria. So we're going to say that we want you to pass from node A through to node B, passing through as many relationships as you need to, and then finding that shortest path function. Okay, so when we run that, I'm just also going to return the return P, and that's going to go and calculate my shortest path. So here you can see that it's decided. Okay, agreed. It's really the same thing. Samuel L. Jackson to Pulp Fiction through Quentin Tarantino. So it's decided to go this way around and through to David Carradine. Okay, so that really sort of is our task here, right? So we wanted to go and figure out that path, but the definition of the Bacon number is actually not the shortest path, it's just the distance of that path. Okay, so what we can do is we can run that same query. Okay, and this time what we're going to do is we just want to return the length of P. Okay, so P is obviously the that shortest path. When we run it, we return that integer. And you can see here that we've got that 1, 2, 3, 4. Now, when we often when they refer to the Bacon number, they don't necessarily pass through the movies themselves. So they would often say it's actually a distance of 2 because Samuel L. Jackson acted in a movie with Quentin Tarantino, who acted in a movie or took in a movie with David Carradine. All right. Now, obviously another option that we might want to use is we've gone through Quentin Tarantino. Now, Quentin Tarantino did not act in Kill Bill, right? Okay, so we might want to apply those kind of filters. So we can go in exactly the same way that we've done previously. We can go and add those label filters to the relationship, filtering actors, and there is only one path, so we know that it should come up with a path to Uma Thurman. And so obviously let's go and show you the actual path. Okay, so here you can see the path. Now, obviously, because it can only go where a relationship type is acted in, so therefore we have to go through Pulp Fiction, Uma Thurman, Kill Bill, into David Carradine. Okay, so that kind of solves our double hop problem, but we don't. If we wanted to ask who has the highest or perhaps the lowest, we certainly wouldn't want to run this through everybody. So exactly like we did earlier when we assigned everybody the role of when we applied everybody the role of an actor in a movie, we're going to apply that same sort of concept, right? So you can see I'm not one for multitasking, right? Okay, so we're going to go in, instead of providing a specific actor, we're going to say, go and give me all actors, right? So I want that whole set of actors, and then I want to go and focus on David Carradine, and I want to go and figure out the shortest distance between these 2 points. I just did a divide by 2 just to get that number there. Okay, so this was the whole, so we counted movies. If I go and run this, we're going to crash, right? And the reason for this is Neo4j doesn't like calculating the shortest path between a node and itself, right? Which, I mean, I get, but I also don't. I would have thought the shortest path would just be 0, right? But obviously, I guess that's just an implementation detail. So to correct this, what we can do is we can add just an additional filter statement. So when we match on actors, okay, we're going to say, well, only run this function where the actor's name is not David Carradine. So that's going to return me a subset for this set, okay? And then exactly like we have, we're just going to go and calculate the shortest path between those 2 actors, okay? And this is going to give me a full list of all the actors as well as their what we might call their Baker number, or in our case, the David Carradine number. Okay, so that does solve our sort of David Carradine problem. Now, the issue I had this morning is I was actually going to run this whole set across the entire IMDb database. Now, like any good presenter, I flushed my database this morning, but it just won't allow me to import it. It didn't like the idea of, I don't know why, because I had done it before. So we just stuck to the subset of data because we want to show who exactly is the furthest distance within the IMDb database. If you guys are interested in doing that, IMDb actually has all of the information available to you. It comes out as a CSV, uncompressed, it's a couple of gigs, but it has every role played by every actor, who directed it, who wrote it, backstage. So it's actually a very interesting data set, and it's great for these sort of purposes, right? These sort of social networking. So that sort of completes my demo. What time are we meant to be finished? Okay, so we are almost on time, I think. We've got a couple of minutes for questions. I'm just going to come back into Slack. Greg asked, is there a result of the shortest last path deterministic? In other words, in your example, you had 2 paths with the same length. Would it always return the same path? If not, is there a way to ensure this consistency? I'll be honest, I don't know. Every time I have run it, it has behaved like that. But I think that might just be something like taking the lower node. Okay, one of the ways, if you needed to get that that guarantee, what you might want to do, I'm not sure how you'd necessarily do it, is you can add weights, right? So we could actually create an attribute with some sort of weight, and we can use that that weight to determine the precedences of nodes. So then you would, and it actually then just becomes that distribution problem, because sort of sorting actors isn't particularly useful in the real world, but where this is often used is for routing applications, right? So if I've got a fleet of vehicles and I need to pass through a number of points, and those points obviously have different distances between them, what is the optimal route, okay? So this is one of the bigger underpinnings within graph theory, is solving that particular problem. And there we would actually be able to give each edge a weight, okay? And then we could ask for the lowest or the highest weight, the sum of the highest weights through the system. So that's how I would do it. I wouldn't do it in this case because it just wouldn't make sense, but yes, you could do it that way. Next question is, Sasha, what would the actual real example of GraphDB to make more sense? So I think I've just answered that. You can ask a follow-up question if you'd like more. Other than specifying the exact node or edge to pass through in reference to my question above. Okay, Greg. Okay, so Greg would just like to know, and Greg, did I answer that question for you? About yes, okay, so he's happy with the explanation of the weights. We could use weights to sort of provide that weight. So I've got no more questions here. I'm just going to check quickly if on the this chat quickly. Could you give a brief description of a practical use case? Okay, so again, I think the shipping option is probably the most practical approach. Yeah, that's kind of that least cost routing, I believe, is what they often call it within logistics. Is now other applications is fraud detection, right? So when we're trying to understand the complex movement of money between individuals, companies, and other organizations, these graph databases can be fantastic for that. The other big implementation is obviously social networks, right? So if we're trying to understand relationships between people, so we have friends, we have family, and we're trying to understand how that interaction might happen. You might think, I'm sure a lot of that happens with this social engineering. The elections are coming up. At least the American ones are. There's going to be a renewed effort to try and disperse sort of information and find people who are more similar, and that can be. I'm sure graph databases are used quite heavily there. Yeah, I think our time is up. I'm just going to read one last question. The actual relationship seems to be maintained, created on each node. Is there something like an implied relationships that are automatically created? Okay, so that's just a question by Elmar. No, there is no relationship between nodes. You'll remember when we created that very first two nodes, they just float out in space. There is nothing relating them. Okay, you might give them the same labels so we can group them in some kind of useful way, but no, absolutely no relationship between them. All right, guys, it's been fantastic. I hope I've answered you some questions. Quick and gentle introduction. Obviously, I'm sure you guys can see that this goes way down in depth and application, but really give it a go. Find a tool that works for you. I've quite enjoyed Neo4j. I haven't done anything useful in it, to be honest. I have used graph databases within SQL. Maybe didn't enjoy them as much, but I think this is just new to me, as it might be to you. So with that said, I'd like to thank you for joining me. Once again, I'd like to thank our sponsors. Okay, I'd also like to thank Rob and Candice for putting on a fantastic event, and I think all the turmoil that they underwent. It's really been a good effort. All right, guys, thanks so much. And I'm Donovan. I'm just going to push the end stop button.